So today my talk is going to have the following 5 parts, and I would like to start with the background and the significance. So nowadays, we know that smart cities is a very hot and well-known concept, which covers almost every aspect of our daily lives, right? From education, transportation, to civil infrastructures. And we say that many of them, if not all, are directly related to structures, right? So in order to make our cities smart, to some extent, we have to fully expand the functionalities of structures. And for example, if we consider all those natural and human-made structures in the spatial dimension, they vary from the millimeter scale to the micro-nanoscale, such as the tower, right? The human hair and the MEMS nanotubes. So many of them, again, are human-made, and there are different strategies to expand the functionalities to touch the limit. One way is from the material perspective, such as we change the materials from natural to composite to functionally graded, right? Those human-made materials. And the other strategy is from the structural perspective, such as in this study, researchers developed the concept to assemble small units together into a big oval structure, such that the oval structure has the same geometry, oval geometries, right? Like the length, width, height, but the mechanical performance could be extremely enhanced, such as the Young's modulus, the density. And we call this kind of structural-based strategy mechanical metamaterials. And my research group has been working on mechanical metamaterials, particularly in the plate-like configurations, such as these two plates. We see that they have basket and hexagonal design patterns, right? So the height, the width, the thickness of the plates is at the nanoscale, and the length and width are at the millimeter scale. In other words, those plates have very large, extremely large aspect ratio, and those aspect ratio, this very large aspect ratio give the plates very interesting performance. Let me give you a quick example. So let's say we have a piece of paper here, and we do this. So when we release, we still have the paper, but it doesn't go back to the original shape because of the permanent damages, right? On the other hand, there are many materials that can fully recover to the original shape, such as cloth, right? But those soft materials are too soft to take any force. So we always want to have something that is rigid and flexible, right? And so here come our mechanical metamaterials. We can see from these images that the axial strain is almost 100% for the plate, right? But it still can fully recover to the original shape. And comparing to the plates that do not have those design patterns, the enhancement of bending stiffness for our plates is up to 10 to the 4th. So next, let's go to the experiments to see how we fabricate those plates. So we particularly use photolithography and ALD techniques to fabricate them at nanoscale. So first, we have the SOI wafer, And then we use HF liftoff technique to remove the middle layer and only keep the top patterned silicon layer. And then we use ALD technique to evenly grow a very, very thin layer on top of the silicon layer. And then we use the etching technique to remove the silicon material such that the whole plate is remained. And here is the recipe of the nanofabrication. And this part is the testing and the characterizing of the mechanical metamaterials for bending stiffness at the micro nanoscale. And so we particularly use a micro-manipulator probe to apply the axial displacement or axial strain, and use the SEM technique to record the large deformation in bending. And in testing, in the fabrication, we fabricate the plates with two types of design patterns. One is the basket and the other is the hexagonal. Okay, so to quick compare and validate the experimental observations, we also develop numerical models using ABAQUS. And here is the comparison. Let me remove it a little bit. Okay, so here is the comparison between the experimental and the numerical, and we see that both the overall deformed configuration and the configurations in detail, numerical and experimental, match each other pretty well. And here is a quick comparison through the whole deformation process. Okay, and here in this part, we also test the tensile performance of our plates and carry out numerical response, both in the overall structures and in details. Next, let's get into the analysis part to develop theoretical models to analyze the stiffness, the bending, and the tensile stiffness. Before really getting into the bending and tensile stiffnesses, we first want to test the Young's modulus of the material, aluminum, because we want to make sure that the Young's modulus is still maintained the same at the nanoscale. In other words, scaling factor, a scaling effect doesn't affect the Young's modulus of the material. And according to our experiments, our testing, yes, Young's modulus is maintained the same. And so here is the theoretical modeling for the large deformation bending. So we have this Darwin equation, and after solving it, we have this nonlinear, non-monotonic moment curvature relationship. And this relationship explains why our plates can fully recover after large deformation. And again, here is the comparison between experimental, numerical for these deformations, and theoretical. In terms of the deformation configuration, we see pretty much good agreements are observed, right? And this part, we study the deformation of the plates under tension. This is because in the transverse direction, due to the hexagonal corrugation, it's non-even, right? So if it's non-even in the height direction, under tension, it's going to behave this kind of out-of-plane deformation. And we hope to study the mechanism behind this. And so we used a rubber to fabricate this place and applied axial loading in tension to see the deformation. So we can see from this figure that comparing to the initial shape, we do have this out-of-plane bending performance. And here is the comparison between theoretical, experimental, numerical, and theoretical predictions. So we see pretty good agreements between them. And this is the enhanced Young's modulus in tension due to the corrugation. And we also compare the stress-strain relations between the theoretical, numerical, and experimental. So after this, we always want to have some so-called optimal enhancement region to combine bending and tensile together, right? And so here is the OER, or this optimal region for the place with a hexagonal pattern. And so people always wonder, so why it has to be hexagonal, right? So it should be able to be designed with other patterns. And in order to investigate that, we also fabricate and study the place with other patterns, such as the cylindrical, basket, and this. And we find that similar observation, optimal enhancement region is obtained. It's always, we can see always here. But comparing to other design patterns, hexagonal is the best. And here this is the comparison of the areal density ratio. Again, the main finding is hexagonal pattern is the optimal, is the best to us. Okay, and next, let's go to the artificial intelligence modeling for mechanical metamaterials. And I think the very first question is that why we want to bring artificial intelligence in mechanical metamaterials, right? So why is it important to us? And my answer is that because nanoscale fabrication and characterization are always very expensive, right? Time-consuming and very easy to fail. So we want to have something that can help us to predict the performance, to help us design, right? And so we use the artificial intelligence techniques mainly for two purposes. One is the performance prediction, and the other is inverse design. And comparing to the whole techniques in the artificial intelligence domain, we particularly use evolutionary computation because this allows us to get the exact expressions based on the input variables and build up the relationship between the variables and the output function, such as in this case, we have the bending stiffness expression and tensile stiffness expression given in terms of the variables. Okay, and next, we always want to test and see the performance, the prediction performance of the artificial intelligence model, right? And so we compare the numerically measured results with the AI predicted results, and we see pretty good agreements between them. And this part is the performance discussion, such as sensitivity analysis in terms of different variables. Because of time, I'm not going to get into details of this part. But all in all, so in artificial intelligence modeling, we have developed an EC-based model to help us predict the performance, mechanical performance of our plates, and also the model can help us do the inverse design, such as if we want the mechanical performance to be like this, how the geometries structures should be, and this model can help us answer this question. So finally, let's get into a discussion, the last part of my talk today. In the discussion, I'd like to give some potential applications, and based on the tunable mechanical response of our plates. This is, for example, we have the application for the bio beams at the millimeter scale, because for let's say wings in the honeybee, the wings should be flexible and light, and also the wings should stand for very extreme, very dense situations, such as the wings conflict, touch a wall and conflict. They should be able to recover to the original shape, right? Should recover the full functionality. And next application could be football wings at the nanoscale for space traveling. And so in this particular study, so we developed this kind of layered mechanical nanomaterials, and it has a top layer. Top layer is based on it's designed for the tensile load, and the bottom layer is designed for compressive loading, and we put top and bottom together, one after the other. So all in all, the structure can deform under both tension and compression. And so here is the force displacement relationship or force strain relationship. We see that we have different post-buckling modes, and more interestingly, based on this design, under both tension and compression, the structure's Poisson's ratio in the transverse direction is always 0, right? And so based on the design of the plate in the middle, so we are able to tune the stress strain or the stress force strain relations to have the tunable mechanical response. And so here is the application in sensing. And next, I will talk really quick about the application in energy harvesting using mechanical nanomaterials. So imagine if we have a plate in the middle, and we place the plate between bilateral constraints and under axial loading. So it's going to buckle, right? The plate is going to buckle to the first mode and the third mode. And through this post-buckling process, the low frequency excitations in loading can be converted into localized high-speed variation, right? So this localized high-speed response can be used to trigger piezoelectric to generate energy. And we see in this design, we have the mechanical nanomaterials and the piezo layer on top of it. So the idea is to convert mechanical energy into electrical energy. And the mechanical energy in ocean engineering or in ocean, could be, for example, ocean wave, to shake the middle part such that the top and bottom plates are post-buckled. And those are the generated electrical power, voltage or power. And eventually, this energy harvesting cell can be used to power, let's say, various sensors for structural health monitoring. And since I'm running out of time, so let me give a really quick summary of what I talked about today. So I talked about the mechanical nanomaterials with tunable mechanical performance and nanoscale fabrication and calibration and mechanical analysis. After that, I talked about artificial intelligence modeling using evolutionary computation and two applications for sensing and energy harvesting. So with that, this is some acknowledgements to the funding sources and my students in my research group, and this is the end.